I would like to take this opportunity to not only talk about the analysis. We are doing this analysis in the framework of a MELODY project, which is financed by the Italian National Astrophysics Institute, and Federico Tosi is here, is the PI of the project, but also to talk about GPR on the moon. And the reason for this is, first of all, because our colleague, Chinese colleagues, gave us a tremendous opportunity, because they sent two GPR onto different parts of the moon. So we have data to think about. I think that the GPR is an important tool and is very suitable for lunar exploration. I actually think that there should be an instrument also in the future available for astronauts on the soil, because it's fast in acquiring data. You can have a fast response. However, as I show you here briefly, there are lots of things that we have to understand. And the moon is a really an interesting place to do this kind of exercise. Okay, quickly, because we don't have much time. This is just to recall you, this is the landing site of CHANG'E-4. Okay, and this is the landing site of CHANG'E-4. Okay, so there were two completely different places. This is the route of CHANG'E-4. You might know that unfortunately CHANG'E-4 after 80 meters just got stuck on the ground. So we have a very limited set of GPR data, unfortunately, because it would have been a great opportunity. Whereas CHANG'E-4 is still collecting data. This is a part of the route. Okay, this is a part of that route we analyze with our colleagues and were published on Science Advances a couple of years ago. And but it's quite interesting the fact that our colleagues made a very precise identical instruments, which is a tremendous opportunity to compare what is working and what is not working, what are results on one side or in another. I'm not going to talk about low frequency. Low frequency has lots of problems. Again, we published a paper on Nature Astronomy last year showing the difficulty to extract reliable data from this channel. However, we are very happy to see that the channel, the high frequency, the 500 megahertz, is working really well. So data can be analyzed and interpreted. And in fact, there are several papers. There are several papers on both the channels. Okay, I'm not gonna discuss about the low frequency. If you want, we can discuss separately about this. I would like to introduce quickly, for the people that are not geophysicists, what is GPR. GPR is a technique that shoots short bursts of energy. This energy is propagating inside the subsurface and got reflected by any dielectric contrast, let's say electromagnetic contrast, and is gathered back to the antenna. So what you have at the end is the section you see here on the x-axis. So you have the position of the antenna, and on the y-axis you have two-way travel time. Okay, the time of flight, basically, of this signal that come back. Just to show you, this is how to see this kind of image. This is a roof of lava tubes. These are data we just collected on Lanzarote in the framework of lava tubes topical team of ESA last May. And this is the lava tube floor. Now, we go to the data from the moon. I can show you the data from CHANG'E-3 and CHANG'E-4. What I've done here, I wrote minimal processing, because the more you process the data, okay, this is something you learn when you do geophysics. The more you process the data, you can have a better results, but sometimes you can confuse things, and sometimes you can create information that is not there. Okay, so the idea is, if you can, to represent with the minimal processing possible, the one you need to represent the data. And here you see the top is the near side part, the CHANG'E-3 data, the bottom is the far side. And immediately you see something, that the penetration of the signal is much higher in the CHANG'E-4 site, okay? You see that all the information, it got stuck in the first 80 nanoseconds, 100 nanoseconds. However, one can ask, okay, I can do some processing and maybe I can extract for the area on top there where I don't see anything, something, okay? So to understand if this is possible, I will show you in a minute what can be done. Just for comparison, this is 500 megahertz on Earth. It's collected on the Etna site with 500 megahertz, so the same frequency. I put here because, as you can see, the maximum penetration in a nice site is about 4 meters. If I go back one moment, on the CHANG'E-4 site, you penetrate 40 meters, okay, 1 order of magnitude more. So this is why GPR is great for the moon. The difference is that because there's no water, the contrast between objects will be dimmer. So it will be much more difficult to interpret properly the data. Anyway, what we can do to understand if on CHANG'E-3 we can process the data and see if we can see something on that. This is a very, very useful plot that GPR experts usually apply to see if there is enough energy that you can improve, that you can use for extract information. And you can see the red line is from CHANG'E-3, the near side. The green line is from CHANG'E-4. And what you see that this is the level of noise. After 100 nanoseconds, CHANG'E-3 arrived to the floor, to the noise. So any process you will do will never bring signals because there's no signal, it's just noise, okay? So anything you can do is process the first 100 nanoseconds and that's it. The rest cannot be recovered because there's no signal, it's attenuated completely. As you can see from CHANG'E-4, CHANG'E-4 goes much higher. In fact, as you've seen in the previous slides, you can see that on CHANG'E-4 you have noise just on the bottom part of your section. So this can create, there are also some high frequency noise that can be removed, but in any case, there's nothing you can do. Unfortunately, in the literature, there are a lot of papers that say they have seen layers here, okay? And this is physically not possible. So this is kind of misinterpretation of pitfalls in the information. In any case, there are information and we have to work to understand what information are produced. This is, just to give you an example, is an attempt to use the information we have, so the top part in CHANG'E-3 and CHANG'E-4 to estimate, for example, the velocity. As you know from equation, Olef equation, the velocity can be correlated with density. So we can have a good information from this. Again, this has been done automatically. And of course, this is too many data, okay? So if we do something automatic, if we do a process that is not correct, we can create lots of data, okay? That should be checked, clearly checked before get used. So in this case, of course, there are too many hyperbolas that has been done with the fitting hyperbolas for velocity. And so there is some information should be checked. Thanks. Again, we can do something for the attenuation. That's what the top is the CHANG'E-4. And this is the calculation for the attenuation and the tangent delta. As you know, tangent delta is a very important parameters because from all of the equation, we can calculate the amount of oxides, iron and titanium oxides. And sometimes in some of the papers, they use the total attenuation, not the tangent delta attenuation, which is confusing again the situation. So as I said before, this can be used to calculate okay, the amount of iron and titanium. So this brief talk, I was trying to point out a few important things, okay? Radar penetration on the moon is generally larger than on Earth. It's quite larger, so it's a really nice geophysical tool. However, there is a problem. The electric contrast is much lower, okay? Because water is attenuate on Earth, but enhance also the dielectric contrast. So it's easier to see layers, it's easier to see things in the subsurface. So we have to be careful when we interpret this kind of data. Some penetration can be small, but small because of the condition, the local condition, not because the radar doesn't work, like on CHANG'E-4, so CHANG'E-3. So we have to understand what's going on. Unfortunately, there are lots of pitfalls and misinterpretation. These have been made, but I think we can learn from our mistakes and make a better interpretation, better use of the data, of course. And there is another point that I would like to highlight, that there is a quantitative relation between what we found, the dielectric properties, and the oxide content or the density. This has been proposed years ago by Oleften, that made a tremendous work. But maybe we have to check carefully if we can improve this kind of equation. Thank you very much.